Hi everybody. Today I thought we would talk about something called Hess's law. So that's our title for today. Hess's law. Okay. Now you may remember from some previous videos some time ago that if we have a formula like A plus B, these are our reactants, and they become our products, in this case C plus D, then sometimes we write down what the enthalpy change is, a delta H value, and maybe in this case it's equal to say minus 300 kilojoules per mole. And what this is called an enthalpy change, and it is a measure of the amount by which the energy has changed as we've gone from reactants to products. So if you wanted to kind of label the energy in the products by HP, and if you wanted to label the energy in the reactants by HR, then if you wanted to write down an equation, you could write down delta, sorry, let's just get rid of that equals, delta H is equal to HP minus HR. But this delta H thing we used when we were looking at graphs for the activation path. So for instance, an exothermic reaction, if this was energy or potential energy up here, and this thing down here was reaction path, then we might have something that looked a bit like that, and this distance here was called delta H. And now don't worry if you can't remember that graph. If you need to revise it, then just go back to one of the earlier videos. So that's really all kind of background, I suppose. The interesting thing, or the thing that Hess's law is all about, is that what he said is that it doesn't matter how we go from A plus B to C plus D, this delta H thing here will always be the same. So it does not matter how we go from A plus B to C plus D. And that's in fact a very important fact, and one that you can use mathematically, and when we do that, it turns out to be something very powerful, I suppose. We can understand things about chemistry that we would find difficult to actually figure out just doing laboratory experiments, which is what makes it so useful. We can draw out what I've just said in green. Let's do it over here. So let's say again we've got our A plus B goes to C plus D, and I'll put a delta H, I'll mark it 1, a delta H1 in there. And in the previous example to the right, that delta H1 was minus 300 as it happens. Well, what Hess's law says is that if instead of going from A plus B to C plus D, we instead went from A plus B to E, and maybe that E has an enthalpy change, let's say delta H2, and then we go from E to C plus D, it has an enthalpy change of delta H3. Hess's law says that delta H1 is the same as delta H2 plus the delta H3. That's what it's saying. And you could make it more complicated if you wanted. Instead of going to E, we could instead make a new substance F, and let's call that delta H4, or that's the enthalpy change in order to get to F is delta H4. And I'm going to go to a substance called G, and that's going to take some amount of energy, delta H5, and then I'm going to go to C plus D, and that amount of energy is going to be delta H6. Well, again, what Hess's law states is exactly the same thing, that this one at the top, this delta H1, let's write that down, delta H1 is the same as going all the way around this circle. So this it's the same as this one plus this one plus this one. So it's the same as delta H4 plus delta H5 plus delta H6. And let's just kind of mark those on with arrows. Okay, and the step that we go to turning this into something that's a little bit more like maths is to realize that these statements, these is the same as statements in maths we just write as this. Is the same as is exactly the same as an equal sign. So if we were to continue the example, what I could write is, let's do it in red. From this one here, I've got delta H1 is equal to delta H2 plus delta H3. So that's just that and that. And the last one we did, I'll underline in black, that one is equal to these three here. So delta H1 equals delta H4 plus delta H5 plus delta H6. So that's how we write it out mathematically, and it's important to know that, but probably what is more important is understanding the diagram, that if we go in one direction from one place to another, it's the same as kind of going round a circle. And if you think like that, then that should help you kind of stay right as you're answering questions on this kind of thing. Okay, let's move on to doing an example on a kind of a Hess's law question. And the thing with these kinds of questions is that they can be quite easy to get wrong, because it's quite easy to kind of make a math slip or kind of get confused when you're kind of going around the circle from one way to another. And what I'm going to do is show you one way of doing it, which is the way that I do it, and it's the way that I understand it, but it may not be the best way for you. So because everybody is different and everybody's brain thinks differently. So if this doesn't work for you, that's fine. Go and find a book, go and find another video, find something else that tells you a different way of doing it that works for you. And once you've found whatever that is, then just stick with it. But I'm going to go through mine, which is the one that, as I say, I like, and the one that I find is most successful with students. Okay, so we need a question to kind of kick us off, and what a question usually does with these kinds of things is gives us a load of formulae and then asks us to figure out something. So I'm going to give us some information here. So we're going to deal with sodium chloride. So NaCl in its solid state, one reaction it can do is it can become a sodium ion dissolved in water and a chlorine ion dissolved in water. That's what the AQ means. And I've got a delta H for that. The delta H here is quite small. It's just 4 kilojoules per mole. Okay, and let's write down another piece of information. Sodium as an ion in its gas state can go to sodium as an ion in its aqueous state, or its state when it's surrounded by water molecules, and the delta H for that is minus 405 kilojoules per mole. And let's do another one. We're going to do something similar for chlorine. So this is all stuff that's given to you in a question, and this is just the beginning of a particular question. So chlorine is a gas, or the chlorine ion is a gas, goes to the chlorine ion dissolved in water, and it has a delta H as well. And in this case, the delta H is minus 376 kilojoules per mole. And what we're actually going to be asked here is, question is, what is the delta H for this equation instead? So NaCl in its solid state going to Na as an ion in its gaseous state plus Cl minus in its gaseous state. So that's the question. The delta H for this is unknown. Okay, so that's the thing that we need to know, and we're going to handle it by doing this going round a circle thing. So the thing that we need to work out, let's just write that out again. So I'm going to start with NaCl as an S, and it's going to go to Na plus as a gas plus Cl minus as a gas. And my delta H, the thing that I want to work out, is unknown. So that's just me restating the question. Let's put a line in between the question and our answer. So this is us beginning our answer here. Okay, so I don't know what that delta H is, but usually the question has given me everything that I need to know to work it out, and that is the case here. So what have I got that's got an NaCl? Because I need to go from here to something else, and then eventually I'm going to get to these two things here. So what have I got in the question that's got an NaCl? And it's all the way up here. It's this first equation here. So this says if I go from the NaCl in solid to the Na plus aqueous and the Cl minus aqueous, I need to put in this 4 kilojoules per mole of energy. So we're going to write this bit out below, and it's going to be the kind of beginning of our circle. So down here, this goes to Na plus aqueous plus Cl minus aqueous. And what was the delta H? Well, up here it's just there. It's the 4 number. So that number there, I'm going to write in delta H equals 4. I'm not going to bother writing the units just now whilst I go through my working. Okay, but we haven't gone all the way around the circle, because if we'd gone all the way around the circle, then instead of having an Na plus aqueous here, I would have an Na plus gas. So I need to somehow get from this Na plus aqueous to this Na plus gas. And similarly, I need to somehow get from this Cl minus aqueous to this Cl minus gas over here. Let's just rewrite that little G there. There we are, Cl minus gas. But we have more information in the question. So here's some information up here. We've got this thing about sodium. But it's the wrong way round. I want to go from Na plus aqueous to Na plus gas, and instead what I've got is Na plus gas going to Na plus aqueous. So I need to flip this equation around, and when we start manipulating equations, we're going to have to change this delta H figure because we're going to change an equation to something else. So one of the things that we can do is we can flip it round. We can say, instead of going from Na plus gas to Na plus aqueous, we can instead go from Na plus aqueous to Na plus gas. And if we do that, so all I've done is written the equation back to front, and if we do that, I have to multiply this delta H by minus 1. So my delta H becomes 405 kilojoules per mole. So that's kind of a rule. Let's kind of write that down. Flip equation round implies multiply delta H by minus 1. And you can kind of see that it makes sense, because what the first equation is saying is that if I go from sodium ion as a gas into sodium ion in water, energy is given out, 405 is given out. So if I want to go in the opposite direction, if I want to get that sodium ion out of water into a gas, I've got to put energy in, and the energy I put in is 405. Anyway, that 405 is just what we need in our Hess's law diagram down below. So now we know that this thing here can become this thing here, and my delta H is equal to 405. And I can do exactly the same with the Cl minus piece of information. So let's flip it round to Cl minus already in water goes to Cl minus as a gas. But if I do that, then my delta H is flipped around, so I need to multiply this by minus 1. So 376 kilojoules per mole. And down in my diagram, I can put that in. Let's do it in green. In fact, no, let's stick with black. So this thing here goes to this thing here, and my delta H is equal to, I've forgotten already, 376. Okay, so what's my delta H? In fact, let's make this just slightly smaller. What's that delta H? Well, that delta H is equal to the sum of everything going round the circle. So that 4 plus this 405 plus this 376. So my delta H is equal to, let's do this with the calculator. 4 plus 405 plus 376. What do I get? I get 785. So my delta H is 785 kilojoules per mole, because when we do our final answer it's important that we write in the units. So that's the energy that we need to put in to take sodium chloride as a solid and break it up into its separate ions in a gaseous state. And you'll maybe realize that it's really important that we handle things like those minus ones, for instance, because if we hadn't changed this 405 from minus to positive, we'd have definitely got the wrong answer. There are other kind of things that you might have to do when you do a Hess's law question. It might not just be multiplying by minus 1, you might have to multiply by other numbers as well. But we'll do that, we'll go through that in a slightly more complicated example in the next video.